Homogeneous transformations. Consider a frame A, a frame B, and a point P. Point P in frame B can be represented with this vector, and in frame A it can be represented by this vector. The origin of frame B with respect to frame A can be represented with another vector t. Now suppose that we have this vector P in B, but we want this vector P in A. So we can obtain this vector by simple vector sum. So this PA will be this vector plus this vector, but both vectors have to be in frame A. This vector is already in frame A, but this one is not in frame A. So we have to convert this to frame A. Actually, we just have to rotate. So this point in frame A will be equal to this T plus this PB, but rotated to frame A. We can represent this in a more compact way as this. Why? Because here we have that PA is the rotation matrix times PB, which is this term, plus this TBA times 1, which is just this one. And here the last row is just 1, 0, 1, 1, just for completeness. We call this first element PA with a tilde, then this one also with a tilde, and they are called homogeneous coordinates. So whenever we have a vector and we add a 1, so it's a 4-dimensional vector, that is called a homogeneous coordinate. And this matrix that relates this is called a homogeneous transformation matrix. This homogeneous transformation matrix represents the position and orientation, which is called the pose, of a frame with respect to another frame. And it has these parts. This is the rotation part, and this is the translation part. Or in compact form, this is R, this is T. This is always 0. Actually, it's 0, 0, 0, and this is always 1. So these two don't change, only R and T are going to change. Rotation and translation or position. Mathematically, they belong to this SE3, which is the special Euclidean, which is the Cartesian product between R3, which is the position, and SO3, which is the orientation. They can also be viewed from the perspective of projective geometry. However, we are not going to deal with projective geometry in this course. Pure transformations would be like this. This is a pure rotation because there is no translation, and this is a pure translation because there is no rotation. Now, be careful, because when there is no rotation, it doesn't mean that this is 0. It means that this is the identity. So, continuing with pure transformations, a rotation about x will be the same rotation about x, but here no translation. Then about y, no translation. About z, no translation. And pure translations will have here the identity, and here, if this is translation in x, I will have d in x. If this is in y, d in y. If this is in z, d in z. The composition. When a transformation is applied with respect to the fixed frame, the composition is exactly the same as with rotation matrices. So it means that we have to pre-multiply. And if it is applied with respect to the current, mobile, or new frame, we have to post-multiply. For example, let's suppose that a frame A is rotated 90 degrees about x, and then it is translated a vector, this vector, with respect to the fixed or initial frame. We want to find the homogeneous transformation that describes B with respect to A. So first we rotate 90 about x, and then we translate. So we rotate first, and then we translate with respect to the fixed frame. When it's with respect to the fixed frame, it's a pre-multiplication. So first rotation, then we pre-multiply this with the translation. We just replace the numbers here, and we get this expression. We have another example. Find a homogeneous transformation that represents a rotation of an angle alpha, followed by a translation of B along the new x-axis, followed by a new translation of D along the new axis, followed by a rotation of the new axis. As you see, everything is about the new axis, so it will be always a post-multiplication. So first post-multiplication, and post-multiplication. Just operate this and we have that matrix. We can decompose now, using this, the homogeneous transformation into the product of two matrices. The first one is just a translation, and the second one is just a rotation. You can verify it easily because it's identity times R plus 0, so just R, and then identity times 0 plus translation, so just T. Using the previous compositions of pre-multiplications and post-multiplications, we can have two interpretations of this transformation. The first interpretation says that we apply a translation of T units, this one, And then we apply a rotation about this new frame. The other interpretation will start with the rotation. So first we apply the rotation, and then we apply a translation, but with respect to the original system, with respect to the fixed frame. Uses. Homogeneous transformations represent the pose, position plus orientation, of a frame, rigid body, with respect to another frame. They also change the reference frame in which a point is represented. So this is a point in B, and this homogeneous transformation matrix takes this point B to frame A. Now the point must be represented using homogeneous coordinates. So we must add a 1 at the end. And the notation that we will use for homogeneous coordinates is this tilde. And the third use is to apply a transformation, a rotation plus translation to a point in the same reference frame. If you see, these three uses are the same uses that the rotation matrix had, but in this case we are adding translation. Let's see an example. Consider frame A and B, these two frames. Point P in frame B is given by these coordinates. We want to find the coordinates with respect to frame A. So we have to first convert them to homogeneous coordinates and then just replace the values. We replace the values here of point P. Then this is the transformation from B to A. Why? Because XB is in minus Y. Here it is in minus Y. YB is in X, so YB is in X, and ZB is the same as Z, so ZB is the same. Now the origin. In X it has minus 4, so it has minus 4. In Y, A, it's 6, so I have 6. And in Z, there's no Z, so just 0. And then I plug the other number, this point which is given, and I get this result. And you can verify this graphically, because we have here minus 4 in X, so this is in minus 4 in X. We have 4 in Y, we have 6, and this was 2, so 6 minus 2 is 4. We have 1 in Z, so we have here 1 in Z because there's 1 here. And then we have the final vector, because in this case, this one is just for the homogeneous representation. Let's see a second example. We have a frame A that is rotated first, and then it is translated with respect to the initial frame. So we first rotate, and then we translate with respect to the fixed frame. So it's a pre-multiplication. Then we consider a point with respect to the new frame, and we want to determine the coordinates of that point with respect to the initial frame. So this transformation is B with respect to A. Now this point is in B, so we just have to multiply it. This is the first transformation, and then we have the point. We have to multiply with this transformation and with this element. We have a frame that is translated a vector 6 minus 2, 10, and then rotated about the fixed frame. So in this case, it's the opposite. We first translate and then we rotate about the fixed one. So this rotation is pre-multiplying this translation. Now we have again the point with respect to the new frame, and the problem is exactly the same. We have to apply this, and we have to replace the transform point and just replace, and we get the vector. If you see here, this result is different from the previous one because this is not commutative. Again, this is like rotations. Translations or homogeneous transformations are not commutative. Let's see some properties. First, the inverse of a homogeneous transformation. If this is the homogeneous transformation, its inverse is this expression. And you can see that this is not the transpose. So for homogeneous transformation, the inverse is different to the transpose. Now, why this is true, this expression? Because let's consider this point B, and we want to express this point B with respect to A. And this is the expression that we obtained in the very beginning. Now I want to solve for P in B. So I want the opposite problem. I want, given this P in A, find P in B. So for doing that, I have to first apply the rotation, multiply it, and reorder this like this. So I'm just solving for this PB, and you get this expression. You can, again, represent this using a homogeneous transformation, and also this using a homogeneous transformation. Now in this case, you can reorder this and see that these terms correspond exactly to this. Why? Because point A is just given by the transpose of the rotation matrix, which is this. And for the translation, I have this R transposed with a minus. The translation R transposed with a minus. The important part here is to remember that the inverse is not the transpose, and it's given by this expression. The product of homogeneous transformations is this one. We multiply the R's, the rotations, and for the translations we apply the first one, and for the second one we apply the rotation of the first one. However, if you do this by computer, you will just multiply matrices and you would not deal too much with this expression. Again, you can see that this is not commutative. Let's consider an example. In this example, we have a robot and a belt and an object, and we have some reference frames attached to different parts. There are some things that we do know, as you can read here, but there are some parts that we don't know. So for example, we don't know this, the pose of the object with respect to the base of the robot, and we want to find it. And then we also don't know the pose of the object with respect to the end effector, and we also want to find that. So we want this object with respect to the base, and then this object with respect to the end effector. Now why? Because if we want to be able to grasp this object, we have to be able first at least to make the frame of the end effector be coincident with the frame of the object. Now what do we know? We know the transformations of the belt and of the robot base with respect to W. So we know these two. And we also know the object with respect to the belt, object with respect to the belt, and the end effector with respect to the base. So we want to find the pose of the object with respect to the base. We want basically this object with respect to the base. Now using the composition of homogeneous transformations, we might want to find something like this. So object with respect to W, W with respect to B, it's like these two W's cancel out and we have O with respect to B. But in the data we don't have exactly this, so we have to use the elements that we do have. What we do have is B with respect to W, which is the same, but we have to apply the inverse in this case. And for this one, I can use as an intermediate frame F, because I have F here, and that's the solution. So the solution would be this one. In the next case, I want to find object with respect to the end effector. So somehow I have to use W as an intermediate frame, and then I can just try to solve for this in terms that I know. At the end, I get this expression. The point here is to use only the frames that I know, to avoid using other frames. Now, as a last example, we have here a table, a robot, an object, a camera, and we have some frames attached to these objects, and we have to find some transformations. So you can just read this example, and the solution at the end is this one. By inspection, we can find these homogeneous transformations that relate each of the frames with respect to the other ones. So this is the rotation and this is the translation. You can easily verify this because here almost everything is 1 meter, 2 meters. So it's easy to verify that. And then you can find the multiplications and use the composition of transformations and find the result. The important point here is that orientation can be represented with 3 or 4 parameters. The minimal representation are Euler angles, roll pitch yaw, and also axis angle. They only use 3 elements, but they have singularities. Quaternions use 4 components and they do not have singularities, and they are the preferred way to represent rotations. Homogeneous transformations represent both position and orientation, and they are fundamental in robotics.